Let's talk about electrons. So far we've talked about protons and neutrons. And protons and neutrons we can think of as particles. They have mass. They're particles. They're in the nucleus. But the electrons are a different story. Okay? A lot of us like to think of electrons as particles. And really we've had a long debate over whether light was particle or wavelength. It exhibits both tendencies. But if we can think of as an electron like a little vibrating spring that vibrates back and forth, string, like a guitar string, electrons are basically a vibration, okay, an energy vibration. Now, Niels Bohr was a Danish physicist who first came up with the idea that we know that protons and neutrons are in the center. Rutherford determined that protons were in the nucleus. And Thomson determined that there were electrons indeed going around or associated with the atom. But Rutherford's like, okay, the protons are in the middle, the electrons are out here. So Niels Bohr is the first guy to kind of talk about electrons. And he said that electrons orbit in a given orbit. Okay? It's like a planet. It's like a planetary orbit. Okay, this was in 1913. In that orbit, you have those electrons going around, and they can only be in certain orbits. Okay, it could be in this orbit, it could be in this orbit, it can move back and forth between them. If you want that electron to move, you have to give it energy. That energy would come in the form of light. Once again, we're going to think of light as a wavelength. Okay, light comes in as a wavelength. It excites this electron and he will jump up to a different energy level. Now, he has to go to an energy level. If he only gets enough energy to go this far, he's not going anywhere. If he gets enough energy to go this far, but there's no energy level there, he's not going. He's only going to go if he gets the right amount of energy. Now, this is just like you getting excited at a football game. You score a touchdown, you get excited, you jump up, woohoo, woohoo, and you get excited. When the electron, he gets excited with it when energy hits him. When he gets tired, he falls back and he releases that same energy that he had before. And that energy goes off. Okay? That is how light is produced. It is produced from that electron, which again is not a particle. It's a little wave. It's a vibration moving between two energy levels. The further out you go from an energy level, the more energy you need. Kind of like if you climb up the rungs of a ladder. And if you think about the rungs of a ladder, if you're going up a ladder, you don't put your foot right here where there's no rung. You can't. Your foot can only be either here or here. Well, it's the same thing with electrons. They can't go halfway in between the energy levels. They have to be on one or the other. Okay? So, electrons produce light, and they produce light after they've been excited and they fall back to their original state, they produce the light. We call that ground state. Okay, so the electrons will start out in their spot as close to the nucleus as they can get. They get hit with energy, they will jump up. And so here's the energy coming in. When the electron goes back to his original state, he's going to give off that energy. That energy is light. That is a wavelength. All right, so here's an example of this. Here we have an electron orbiting a nucleus. Watch what happens. I'm going to use my mouse, and I'm going to click on an energy level further out. Watch what happens to the electron. As I click, you'll see coming in from the bottom the energy. And when energy got to the electron, it jumped. So he's gone from the first level to the third level. Now, if I click the first level again, when he falls back, watch, he's going to release energy. And did you see it? It was right here. Let's try it again. Here comes the energy. There it goes. Okay? If I go a bigger jump, there goes the energy. It was hard to see. It came off the bottom here. Okay? I'm going to go to this level, and then I'm just going to go down one level. Watch what happens. Did you see that the energy level color changed? The color was kind of a yellow. If we come in, it's going to change too. We're going to relate that to visible light here in a minute. Okay? So this is what's happening. This is how light is emitted. Light is emitted by electrons moving back and forth and giving off that light energy. Okay? All right. Light energy occurs in waves. Okay, it's got a wave-particle duality. It's both wave and particle. It acts like both, but we're going to treat it as a wave. Now, in order to do that, we need some vocabulary. The parts of the wavelength. Wave. The crest is the top part. The trough is the bottom part. Wavelength is the distance from one crest to the next. The amplitude is the height from what we call the resting point to the top of a crest. Okay? Why is that important? Why are these important? Well, wavelength is directly related to another property of waves called frequency. Okay? If I'm waving, okay, I've got a long wave, and we count how many waves I do. The number of waves that I do is going to be frequency. Now, as my waves shorten up, what happened to my frequency? My frequency increased. So, waves, wavelength, and frequency are inverse. As one goes up, the other goes down. All right? So, as wavelength increases, frequency decreases. Again, low frequency, long wavelength. High frequency, got to keep it in front of the camera, short wavelength. Okay? That's an inverse relationship. If we multiply them by each other, we happen to get the speed of light. And the speed of light is always the same in a vacuum. The speed of light is 3 times 10 to the 8th meters per second. That's 2, 3, 4, 5, 6, 7, 8, 300 billion meters per second. That's how fast light moves. So if we know a wavelength, we can figure out a frequency. If we know that the speed of light is 3 times 10 to the 8th meters per second, and we know a wavelength, we know how long a wave is, we can figure out a frequency and vice versa. Now, instead of using the words wavelength and frequency, because this is physics, we have to use the little Greek letters. This upside down Y is wavelength. I think it looks kind of like a wave, a breaking wave in the ocean. All right? Frequency is shown, this is the Greek letter lambda. Frequency is shown with a V that to me looks like it's been vibrating back and forth and it's blowing in the wind. Okay? So wavelength and frequency can tell us how long a wave is. Why do we want to know how long a wave is? Well, it depends on, there's a lot of different things that are associated with wavelength. For instance, this is all the different types of light. Notice, we have radio waves down here. You guys listen to the radio all the time, or maybe you don't. I don't know. You may just listen to your iPods, but I still listen to the radio every morning. Radio waves aren't going to hurt you. Gamma rays, on the other hand, are what's released in a nuclear reaction. Okay, if you are standing next to the nuclear reactor at a power plant, you're going to be exposed to gamma radiation. That's why they wear the funky suits. Gamma radiation has so much energy that it can penetrate straight through your body, into your cells, into the nucleuses of the atoms of the cell. When they had the Chernobyl explosion in 1986, they told women who were pregnant over in East Eastern Europe to stay inside because there was gamma radiation in the air from that explosion, and gamma radiation can affect growing cells. Well, what's a baby? A pregnant woman's got a baby. That's all growing cells, and they're growing at a rapid rate. So they told the pregnant women, stay inside, don't go outside. Okay? Gamma radiation, very harmful, very high powerful. Notice the length. 10 to the negative 16. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 meters. That's the length, the wavelength of a gamma ray. Okay. Next in energy is X-ray. Gamma rays can go all the way through to the cell level. X-rays only go through to the bone level. They don't go through the bone. That's why X-rays are great for showing broken bones. They still are involved with radiation, and you still don't want to be exposed to them day in and day out. That's why when you go to get an X-ray, they put the big heavy lead diaper on you, or on the apron on you, like in the dentist's office. I had a student once who was so excited because he'd had to have an X-ray of his leg or something, and he came back to school and told us all about how they put a lead diaper on him to protect his family jewels, if you will. And I think he actually called it family jewels too. Next is ultraviolet. We know ultraviolet radiation comes from the sun, but we have this lovely layer that protects us from that. Although we don't anymore. It's much thinner and it doesn't do as well, so we have to add sunscreen. Sunscreen protects us. You put it on that top layer, and that ultraviolet radiation gets absorbed by the sunscreen. If it's not there, it goes through and is absorbed by the top layer of skin. You get a bad sunburn, it's because it's gotten too much energy. Then we get to visible light. Then we get to infrared light. Infrared is heat. All those movies where they're using the heat sensor things, those are all using infrared light. Microwaves are the waves that they basically are big enough they excite molecules in your food and get them excited. They excite the water molecules. And then radio waves, notice they're 100 meters long. A microwave is about a centimeter long. Okay? All these are different types of waves. Now I want to share something with you. Okay, I'm going to teach you a song. Before I teach it to you, I want you to see this tweet. Okay? Hannah Stace, who graduated this past year in 2016, she said she sang the electromagnetic song in her college chem class in order to remember the order. She's not the first student that has told me that, but she's the first one that's tweeted that. Okay? Why is that important? Well, we're going to learn a little song. This song was made up by Scott Young and Spencer Booth in about 2000, 2001. They made this song up to remember the electromagnetic spectrum. Now, it starts from the right and goes to the left. This is the way it goes. Gamma rays, X-rays, ultraviolet too. Visible, infrared, microwave the food. Turn on the radio and dance a little too. Okay? So you're all going to sing it with me. You ready? Gamma rays, X-rays, ultraviolet too. Visible, infrared, microwave the food. Turn on the radio and dance a little too. Okay? That is one way to remember the electromagnetic spectrum. All right, we've covered light, we've covered energy with light, we've covered wavelength. We haven't done any problems with it, but we're going to stop here because we're almost out of time anyway. And so there you go.